I think Dan killed the meeting early. Dan, did you click the X?
I I didn't think I clicked anything. I have no idea.
I think Ahmad was in here. Maybe it switched to him as the host and then he left.
Oh, that might be it. That might, yeah. He was probably the host recording it, and then he left and
Everyone back?
Still here.
Yeah.
What was I talking about? Oh yeah. So like for decompression, right? Basically decompression is like some other processor you have to build in to like the ASIC, right?
Exactly. And my understanding is historically, it's just GPUs are terrible at that, which is why no one's tried to do this, because you need a separate chip basically between like after the PCI Express, but before going into the GPU.
Right. So at least kind of what I see now is like the push is more like, okay, increase the memory interface. So like more HBM
Yep.
close to the chip, increase the number of PCIe lanes,
Yeah.
or increase the number of backend network connections. So
Yep.
like either that's more PCIe lanes if you have like a RDMA system, or on some of these ASICs like that Meta is developing, you actually have like Ethernet lanes coming out of the ASIC.
Yep.
So like just put more of that basically is better use for power and
Yep.
die size and overall board design, as opposed to like putting a like decompression engine, because they would have to also be a very fast compression engine, right? So
Depending though, if you're trying to do like 10 gig wire rate, I think there's stuff that's been out there for a while. There was some, I
well,
want to say it was somewhere out of Canada. They were doing this in FPGAs like 10 years ago. Because we used to look at it for real-time compression of data. Because again, we're trying to capture all these raw Ethernet packets at, like
right.
way beyond 1.6 terabits worth. And then how can we stream that efficiently? And typically it's trying to then get it into an x86 machine to write it. But if we could compress it ahead of time, it could be worth looking into. I mean, this would probably be more like a, well, I don't want to say your competitor, Dan, but there's a certain company that does both CPUs and still owns an FPGA company. I don't know what the nature of the relationship now is between Intel and Altera, but
Yeah. No, we still, I mean, they're still an Intel company. They're just trying to spin them off
gotcha.
as a subsidiary or something like that.
But it'd be interesting to see. I mean, and definitely do everything that Julian was saying as well about all the different ways you can parallelize it and increase the bandwidth. But then on top of that, if you throw compression, depending on some of these data types, they compress massively well. I mean, even using some like the fairly simple tech.
Yeah, I mean, one of the things that we've talked about is spraying, right?
Yep.
You could spray the data, and they do that, right? So,
DSF, the fabric that Meta uses, actually that's something Ultra Ethernet is talking about, but that's why Meta uses DSF, is because the switches they have a layer above Ethernet, the cell network that does the spraying. So if you have 800 gig links, it actually spreads across the 800 gig links, as opposed to Ethernet, which will kind of like go one.
Makes sense.
So,
and you would also mentioned with Facebook, they're doing ASICs. Have they ever looked on photonics on chip? I know we've been waiting for this from Intel for 10 years. Very excited for it. Always next generation. But if you can start doing like
always seems to be 10 years away for some
right?
reason, or 5 years away.
Yep.
And so
this is the year. Come on. Or at least the decade. I don't know. Hopefully.
well, the year's running out, so it might not be the year at this point.
Yeah. I doubt it's the year. But...
Okay. All right, we're getting close to the end. Any other questions or comments?
And I'll give the floor to someone else too. I don't want to hog it.
Okay.
I don't want to saturate the bandwidth of the link. That'd be sacrilege.
I think we lost a lot of people when we got disconnected. But yeah, we'll have the recording and people can ask. But basically we're looking for people to work on these kind of projects and get us the data, right? It's easy for myself, Ahmad, Julian, to say, guys, it's obvious. It works for video. It's going to work for AI and ML, right? But until you can get the data in front of the decision makers, it's a hard decision. It's like we could just go 10 times faster next generation and everything's great. But you look at these pictures and you say, well, why couldn't I even this out a little bit better, right? Why can't I, even a simple scheme like a TDM, right? You only have this bandwidth during this time, or you can only communicate between A and B or this route for this amount of bandwidth over this amount of time. And, you know, I think even simple things like that, where you're looking at it. I personally think that time, you know, protocols are going to be time aware, right? The Ultra Ethernet will be time aware. I think RDMA and NVMe, they're going to have start this transmission at this time. You know, the receiver and the transmitter may have to negotiate when this is going to happen, right? I can only receive this during this time, so only send it at that time. And I can only receive at this rate, so send it at this rate.
Yes.
And you know, knowing when the stop of a certain flow is going to happen means you can set up the next flow. Okay, this flow is ending at this time. I don't want to waste bandwidth not getting the next flow going across. And so, all right. Any other words, Julian or David?
No, it's a very interesting problem, and it's one that I think a lot of different industries have, and we're all looking for different ways to grapple it. The one advantage you all have is you're all trying to coordinate your same machines. It's not a bunch of direct competitors who all want to be the one to get there first, so they don't make any money.
Right. Yeah, that's true.
I think that's the nice part kind of about the AI
That's why I like
network
this.
problem.
Yeah, it's more
'Cause-
collaborative.
Yeah, that's true for all of these AI training, like Meta, Google, Microsoft. When they're running these large training jobs, they're running them themselves between machines that they're owned, and all the machines are running the same job at the same time. So they're all kind of already talking collaboratively. So that kind of bounds the problem space. Like you said, like if you have like 10 processes all trying to use this like common network, okay, how do you arbitrate that? But if you're all just training one job, then okay, you can say like, okay, you only talk there and you talk there.
And I'd be curious, I need to research more about it, but I would think thered be something like this similar even in the operating systems community of just how they do scheduling within a single CPU, and you don't get too much thrashing between threads, processes, whatever it is, whether that's disk scheduling, CPU utilization, memory allocation.
Yep.
I don't want to say definitively, but it seems like, again, like a similar problem, but just it's at a different layer of the stack of, you know, different wires and bits.
I think there, because the latency is so low, like if you have a hardware semaphore, right, you don't have access latency. Whereas here, if you have an 800 gig network, in the time that it takes me to send you a packet and you send me something back, I could have sent like 100 gig of data or something, right? So like or whatever. But you know, like that kind of like plays into the problem, right? That's why I kind of don't like these reactive like ECN or PFC methods where you know, you tell me to back off, even if you only tell me to back off for like a millisecond at 800 gig is like a huge amount of data that I just wasted, right? So you can't like rely on these kind of like reactive methods and then you already lost so much performance. Whereas like inside a CPU, it's kind of designed to, you know, you have one core trying to access something another core wants, you have a semaphore or some atomic operation scheme. It's local, you can access that same atomic variable and say like, okay, my lock is not myself. But over the network, once you go between machines, then your latency is kind of bounding that feasibility, I would say.
Makes sense.
So I have a hard stop at 5. If you guys want to keep talking, you know, feel free, but I have to drop. Or we can conclude here.
No, this was excellent. I just thank you for putting this together, and hopefully some of my students found it interesting as well. They're currently picking their projects. These are exactly the sorts of things we look at, and just how to do ultra precise timing, time synchronization, time distribution, dealing with these saturated networks. How do we capture all this data? So this was great.
Cool.
Awesome.
Well, thanks everyone for coming.
Yeah, thanks guys.
And Julian, it was great to meet you for the first time.
Yeah, nice talking with you, David.
Pleasure. Take care.
Right,
see you guys.
Bye-bye.
Thank you.